Most of us remember the feeling. Sitting in a stiff chair, staring up at a chalkboard while a teacher told us to memorize a squared plus b squared equals c squared. We're often handed these equations like they were carved into stone by ancient, untouchable geniuses. We're taught to simply accept the rule, memorize the formula, and move on. But you don't actually have to take their word for it. There are hundreds of valid ways to prove this specific theorem on your own, using nothing but logic. Real mathematics is an active human process, a continuous investigation into how simple pieces fit together to reveal a larger truth. To see what that looks like in practice, we can leave ancient Greece and jump to 1876 in the United States. Before James A. Garfield became the 20th president, he was a working politician who spent his free time playing with paper cutouts. He didn't use massive, complex calculations. He just took very basic concepts he already understood and started piecing them together in new ways. It turns out you don't need an intimidating formula to stumble onto a great insight. Sometimes all you need is a little low-stakes playtime. Here we are looking at a simple technical diagram showing two identical right triangles. Their sides are labeled A, B, and C. A triangle's area is 1/2 its base times height. Following Garfield, we duplicate our triangle, turning it 90 degrees. We slide them together, aligning their bases flat. Finally, a single line bridging the top peaks creates a third empty triangle right in the middle. This completed diagram outlines the final result. The outer boundary we've just sketched out forms a single standard trapezoid that perfectly encloses our three inner shapes. The total physical space inside this outer trapezoid is composed of our three smaller triangles. Because of that, the area of the large shape must equal the sum of its parts. To calculate this mathematically, this slide lists the variables we need to find the area of a trapezoid: the top, the bottom, and the height. We place the trapezoid's formula on the left and the math for our three triangles on the right. Because they represent the same space, they balance. Applying basic algebra, matching terms cancel out. The remaining letters slide into place, revealing a squared plus b squared equals c squared. No one pulled this theorem out of thin air. It physically builds itself when you let simple, indisputable facts interact on a page. Garfield eventually published this proof in a regional education journal. It's a great reminder that mathematical ideas are living cultural artifacts, driven by curious people. When we teach students to blindly trust a final equation without letting them see how it's built, their understanding becomes incredibly fragile. The moment they forget one letter, the entire concept collapses. Prioritizing the underlying logic gives students the tools to reconstruct answers from first principles. They begin to experience the geometry as a form of spatial exploration. As the text on this presentation slide suggests, our goal in education should be to read, research, and rebuild the historical narratives behind these concepts. When we frame learning as using what we already know to explore the unknown, the intimidation fades. It just becomes a solvable puzzle.